So, hello and welcome back to my channel. And after we already get to know about the basics of system verilog, and in the previous session, which is like yesterday, I get to know the tasks that we would like to be doing, realizing, which is like calculator. So we wanted to take the steps as a hardware design engineer in order to perform the tasks, all right? So starting from the requirement, I think the requirement is very clear. I will show it again. It should be yes. So this should be the requirement. So calculator will accept multiple number numeric inputs, which means that um you input, like the user can input number one and number two, right? Um, or basically the user can add 15473 plus 2234, right? So this 15432 to this all 1532, this is all is a number that is input, is going to be input from the user. And of course it has to be saved in kind of a FIFO, for example, to take the number one and then seven and then three and then two, and then so you write it down in the FIFO, and then while performing the calculation you wanted to read it out, all right? So this is something to be taken into consideration. um, So, and then we need to store it, store the inputs, which is, yeah, if we wanted to store, then we wanted to use FIFO, and then perform a operation, which is the ALU. So now I'm thinking of what could be models that is used in order to perform the task. So, of course, then ALU, we need to have, then afterwards, an ALU. Oh, Ali, hello. Thanks for your comment and for the like. So again, so one module would be FIFO, the other module would be ALO, and then we just show out the result. So in order to be able to perform that, of course, the ALO is very easy because it is simply you're gonna be receiving the numbers in integer, and then you're gonna be having kind of a switch case to yeah, I even made it here. um so here you're gonna be having here the operand one, operand two, and operator, and then there must be a switch case in order to switch from between the different operator and then having the result. But the question is the FIFO. So of course the FIFO should has the output of operand one. So looks like we have a FIFO one, and then we should have e5 2, and then yeah, I think we should then need e5 2, in which the result should be like yeah, I think output and here input. So we're gonna be reading, and then this should be the output. So this is 5 2, and this also has output is output, the number output, and then this should be like the output from here, and then the output from the other FIFO. And I'm not sure if we need another FIFO for the operand, but I believe maybe the operand comes directly from the user, from the output user. um, yeah, so like from other modules, right? So we will be focusing on to making the um, yeah, I wanted to show. Hmm, we show the entire screen. All right. So, so this is in general what I thinking it should be. Like we have here a FIFO one, and here FIFO two, and then the operand comes from the outside, and then here will be switch case in order to perform the task. But of course, let me dive deeper into a FIFO, how to create a FIFO in the um, how to create a FIFO. I think it must be this one, FIFO systemverilog. Let me first get. Okay, so this is looks like this is a complete tutorial of FIFO.
Hello everyone, I am Kundan and today we will deep dive into super important topic that is asynchronous FIFO design and its verification in system Verilog. Here is the content of the slide. First we will see FIFO and its types, then block diagram and control signals, asynchronous FIFO concepts like metastability, synchronizer, FIFO depth. Then we will see design concepts like full, empty, read, and write. Then we will see the design code, then system Verilog test bench architecture, then various test benches for verification, and then finally waveform and its result. Now, what is FIFO? FIFO stands for first in, first out. It is a memory or buffer that ensures the first data retained is the first data to be read. Here is the use cases of the FIFO. FIFO is used in the clock domain crossing, that is transfer the data between the blocks running at the different clocks. It is used in data buffering, a smoothness of data transfer between the producer and the consumer. It is used in the rate matching and in serial communication like in
Clock domain crossing, transfer data between clocks running on different clocks. Use case of FIFO, yeah. Yeah, so it's FIFO saving, yeah. So basically sometimes we have a different clock domains, and then we wanted to either reduce the speed of reading or writing data. So we use FIFO for that. Data buffering, smoothing data transfer between product and consumers, rate matching, balance data rates between fast and slow, subsystem serial communication, UART, SPI. Um, yeah, so in UART, of course, we need it. In SPI buffering, also we need a FIFO. And the pipeline staging, holding data in pipeline for
part
digital
or
design.
SPI buffering and in pipeline staging. It holds data in pipeline digital design. Type of FIFO. FIFO is categorized into two types. First is synchronous FIFO and second is asynchronous FIFO. In synchronous FIFO, both read and write operation is done using single common clock. But in asynchronous FIFO, uses separate clock for read and write. Now why asynchronous FIFO is needed? Let's say your CPU is running at 1 GHz and your peripheral is running at 100 MHz. How will they exchange data reliably? There is where asynchronous FIFO come in. Let's see the block diagram of asynchronous FIFO. Here is the control signals of asynchronous FIFO. Here is data in, the data to be write. Data out, data to be read. Read enable, write enable. Write clock for the write clock domain, read clock for the read clock domain. Now we have two handlers, write pointer handler and read pointer handler. Write pointer handler will generate full flag and a read pointer handler will generate empty flag. Write pointer handler will generate two pointers, binary write pointer and gray write pointer. The read pointer will generate two pointers, binary read pointer and gray read pointer. Now we will pass gray read pointer in the write clock domain and gray write pointer in the read clock domain. Now what is this? We will see in the next slide. Here is the control signal that I have already explained. Now what are the key? Here is the control signal.
So basically, we have here the write enable and read enable, write clock and read clock, write data and read data, write reset and read reset, FIFO and FIFO.
That I have already explained. Now what are the key challenges in the asynchronous FIFO? First is metastability because data crosses clock domains. Second is pointer synchronization. Read and write pointers need to be updated safely.
So let we continue with the tutorial. asynchronous FIFO. It is stability due to clock domain crossing. Save pointer synchronization. Write pointer in read clock domain and vice versa. Full and empty flag generation without time error.
And third is full and empty detection. Tricky because clocks are independent. Now, what is metastability? Metastability occurs when a flip-flop receives a signal too close to its clock edge, violating setup or hold time. As a result, the output becomes unstable, neither a logic 0 nor 1 for an unpredictable time. For example, see here, this is the setup time of the clock edge and it is the hold time. If some data comes in between this, then it will violate the setup or hold time, and that data will go to the metastable state. Clock domain crossing. Clock domain crossing refers to the transfer of data or control signals from one clock domain to another clock domain, which are running at different frequencies or spaces. For example, in our asynchronous FIFO, both read and write both are working in different clocks. So why clock domain crossing is challenging? Because time is unpredictable, because clocks are asynchronous, signals can arrive mid-transition, leading to metastability, causes glitches, data corruption, functional errors if not handled properly. Metastability solutions. We solve the metastability problems by passing it through two flip-flop synchronizers. Now, what is two flip-flop synchronizer? It consists of two D flip-flops. First, data is passed to first D flip-flop, then to the second D flip-flop. Then we get the stable data. The first flip-flop may go to metastable, but the second flip-flop will capture the stable output safely. Now, passing the pointer from one domain to another domain, we use gray code pointer. Why gray code? Because gray code ensures only one bit change at a time. It reduces the chance of invalid transition during the synchronization. It also reduces the metastability. For example, when the value changes from 3 to 4, in case of binary, it changes 3 bits. But in case of gray code, only 1 bit goes from 0 to 1. So it reduces the metastability. Now let's see how it is working. In asynchronous FIFO, we pass the write pointer in gray code to the read clock domain and read pointer in gray code to the write clock domain. Then we synchronize them using two flip-flop synchronization. Write pointer is synchronized into read clock domain and read pointer is synchronized into write clock domain. The question arises why pointers are actually exchanged. Pointers are exchanged between domains to detect the full and empty status. This ensures FIFO does not overflow or underflow during asynchronous operation. Now let's understand the complete picture. FIFO does not overflow or underflow during asynchronous operation. Now let's understand the complete picture, how the FIFO is working. For FIFO, we have data in and data out, data in for write and data out for read, write enable and read enable, write clock for write clock domain and read clock for read clock domain. we have two pointer handler, write pointer handler and read pointer handler. The write pointer handler will generate two pointers, binary write pointer and gray write pointer. Read pointer handler will generate two pointers, binary write pointer and gray read pointer. Now, gray read pointer is passed to read pointer handler. Now, gray read pointer is passed through two flip-flop synchronizer to the read pointer handler. Because it is passing from one clock domain to the next clock domain, so we need to pass through the two flip-flop synchronizer to remove the metastability. Similarly, gray read pointer pass to the write pointer handler by passing through two flip-flop synchronizer to remove the metastability. Now, here we have write pointer and read pointer. By comparing them, we detect the full flag. And in the read pointer handler, we have read pointer and as well as write pointer. We will compare and we will detect the empty condition. This is the actual diagram. Now, what is FIFO depth? FIFO depth simply means the number of data words the FIFO can hold at a time. Why FIFO depth matters? If we choose wrong depth, that cause serious problem. For example, if we take depth too small, then it will cause overflow and our data will be lost. And if we take depth to be too large, then it wastes area, power, and increase latency. So we need a balance, not too big, not too small. Here is a question on the FIFO depth. For example, in this question, frequency of write is 100 MHz and frequency of read is 50 MHz and our burst data is of 100 bytes. Now time taken for one write it will be 1 upon 100 MHz, that is 10 nanoseconds. Now for 100 bytes burst data, time will be 100 into 10, that will be 1000 nanoseconds. Data will be 1 upon 50 MHz, that will be 20 nanoseconds. Now in 1000 nanoseconds, byte rate will be 1000 upon 20, that is 50 bytes. 100 bytes of data is coming and only 50 bytes of data is read. So our depth will be 100 minus 50 is equal to 50.
Fifty. Yeah.
Now let's move to the design part of our asynchronous FIFO. Here is the logic for empty and full flags. Full and empty flags are generated using the difference between write and read pointer after synchronization. Now the key idea for finding the empty is that if both the pointers are equal, then we consider that our FIFO is empty. And for full, if write pointer is equal to read pointer with MSP inverted and LSB same, then we consider the asynchronous FIFO to be full. Now let's see the design code of asynchronous FIFO. We have used the parameterized way. I have taken data width as 8, address width as 4. Now for the write domain, we need data in, write enable, write clock, write reset, full flag. For the read domain, we need data out, read enable, read clock, read reset, and empty flag. Now we need depth. Depth is calculated as 2 to the power address width. That is 1 left shift address width. Now we declare the memory of our required data width and the depth. Then we need two pointer, write pointer and read pointer. For write pointer, we declare binary write pointer and gray write pointer. Similarly, for read pointer, we declare read binary pointer and read gray pointer. Now here is the synchronized gray pointer for both read and write. Write operation always at the rate process of write clock or process of write reset. That is, we have used asynchronous write reset. When reset will come, then we will make all our pointer to 0. Else, if write is enabled and FIFO is not full, then we will store the data in to the required address and we will count +1 to the write pointer binary. And then we convert it into gray. Then we synchronize the read pointer into the write clock domain. That first we pass through first clock, then to second clock. Similarly, for the read operation, at process of read clock and process of read reset. If read reset, then we make all our pointer to 0 and data out will be 0. If read enable is high and if it is not empty, then we take out the data from the required address and we count +1 to the read pointer and make gray pointer from it. Then we synchronize the write pointer into the read clock domain. That we first we pass it through first clock, then through the second clock. Now we will convert the required gray to binary. Here is the function. Here the pointer we receive in gray pointer. First we convert into binary, then check the full and the empty condition. Now let's move towards convert into binary, then check the full and the empty condition. Now let's move towards the test bench using the systemverilog. Systemverilog supports powerful features like class randomization, coverage, assertion, and loops, all of which make test bench scalable and reusable. Here is the test bench architecture. It consists of generator, transaction, driver, interface, duty, monitor, then transaction, and a scoreboard. Now I will explain each term. Generator generates a stimulus and send it to the driver using transaction. Transaction is just like a packet. It consists of data to be sent and data to be received. Then driver send it to the interface. It is just like a helping hand and it passed to the interface. Now come to monitor. Monitor is a passive element and it only observes the output from the interface and it passes its result to the scoreboard using transaction. Now scoreboard compare the actual result and the expected result and it will tell us that our test case passed or failed. We will move to its code one by one. Here is the flow diagram of our architecture. Generator generates the stimulus, send transaction via mailbox to the driver. Driver drives interface signals. Then it goes to monitor. Monitor reads interface signals, sends observed transaction via mailbox to the scoreboard. Then a scoreboard computes expected and compared with the duty result and tells us that our test passed or failed. Now let's move toward the code. Here is the interface code. Interface FiFo if we have used the parameterized way. I have taken data way to be 8 and then write clock, read clock. Then here is the DUT input and DUT output. Data in, read reset, write enable, and data out, full flag and empty flag. Then I use modport. Modport is used to provide direction and end interface. Here is the transaction class. Transaction class consists of data, write enable, read enable. We make it rand because we will use randomization. And then here is the expected data. We make constructor, default constructor, data is set to be 0, write enable to be 0, read enable to be 0, and expected data to be 0. And here is the display statement to display which class is currently running. Then we make a clone of the transaction which is used in the monitor, and we make a compare function which is used in a scoreboard to compare the actual data and the expected data. Generator class. Generator class consists of two modes, 0 and 1, which is represented by with random mode, 0 for user defined and 1 for random. Then we need queue for the user defined, mailbox to transfer transaction from the generator to the driver. We by default take number of transactions as 10. Here is the constructor. We initialize mailbox and take random mode as 1 by default. Here is the task to add the user defined transaction to the queue. Now here is the run function. Now we first initialize the transaction. If it is random mode, that is 1, then we repeat number of transactions, that is 10. Then transaction is created by tr.randomize, and we put the value generated into the mailbox and pass it to the driver. If it is not random mode, that is it is user mode, then we take out data from the queue and put it into the mailbox and we pass to the driver mode. Now we will see the driver part. Now the data comes to the driver. Driver will send the data to the interface. Now let's see its code. Class driver, it will instantiate interface and the mailbox. Here is the constructor where we instantiate the mailbox and the interface. Here is the run task where the driver takes data from the mailbox by using the command .get. Now there are two operations, write operation and read operation. For write operation, if read enable is 1, then it will check if FIFO is not full and FIFO is not at write reset, then it will make the read enable as 1 and data in as transaction.data. It will simply pass the data from the transaction to the interface. Now at the next passage of clock, it will make the write enable as 0 and display the statement. For the read operation, if read enable is 1, then after some delay, it will check the FIFO is not empty and FIFO is not at read reset, then it will make read enable as 1. Then at next passage of clock, we will make read enable as 0. Then we will display the statement. Monitor observe the data from the interface and pass it to the core. Now let's see the code for monitor. Monitor, required interface and mailbox. Here is the constructor where we initialize interface and the mailbox. Then we run monitor write and monitor read in parallel by using the for join. Here is the task for the write and here is the task for the read. For write, task monitor write, we make transaction tr, then run a for ever loop. Then at passage of clock, if write is enabled and memory is not full, then we make a new transaction and make write enable as 1. Then we put the data from the interface to the transaction and put the transaction in the mailbox so that it can be passed into a scoreboard. Now for read, we make task monitor read, then we declare transaction tr, then we run forever loop. Then at the next passage of clock, we check if read is enabled and FIFO is not empty, then we make a new transaction tr is equal to new and make read enable as 1 and take the data out from the interface to the transaction and put it into mailbox so that it can pass into a scoreboard. Now let's see the scoreboard. Now in the scoreboard, we compare the expected data and the actual data, and it tells that our test is passed or failed. Let's go through its code. Here class scoreboard, then we take parameters, data width is equal to 8, then we take the expected queue, queue for write the expected value, and mailbox that we receive from the monitor. And here is the constructor. Now task run, we declare a transaction TR and then we run whatever loop. Then we take data from the monitor. Now there are two operations, write operation and the read operation. For write operation, we push the value to the expected queue so the data can be compared. Now if we read operation, read is enabled and write is not enabled, then if expected queue is greater than 0, then we compare the value from the mailbox and the expected queue. If it is not equal, that means our test case is failed. If it is equal, that means the our test case is passed. If the queue is not greater than 0, it is less than 0, it means it goes to underflow, read occur with no expected value. So here our scoreboard tells that our test case is passed or failed. This is our top module where we include all the modules like interface, transaction, generator, driver, monitor, scoreboard, and environment. In top module, we take parameter data with a state and array with a score. Then we instantiate the interface. Then we generate the clock for write clock and the read clock. Then we connect our test page to the DOT, and here is the code for wave generation. Now let's see the different test plans to validate our rules. So for that, I use 9 test plans. Reset test, then one write, then read test, multiple rewrite test, overflow condition, underflow condition, random write and read, wraparound test, apply reset at middle, simultaneous write and read. First is reset test. For reset test, we make write reset as 1, then read reset as 1, and write enable as 0, read enable as 0, data in as 0. And after some delay, we make write reset as 0 and read reset as 0. Now let's see it waveform. Here we make write reset as 1 and read reset as 1. Then after some delay, we make it 0, and our FiFo is empty. Empty is 1, FiFo is 0. Now our second test plan is to write one data and then read it back. So here we make write enable as 1 and read enable as 0. Then we take data as 42. Then we read it back by making write enable as 0 and read enable as 1. Now let's see it waveform. Here we write one data and read it back. Write enable is 1 here, so it will write here, and here read enable is 1, so it will read. Multiple write and read test. For that, we take a for loop and write 4 data to our FIFO and then read it back. Let's see the form. Here we have written 4 data 0, 1, 2, 3, 4 and then read it back. Then our data is coming correctly. Overflow test. Now our FIFO is of size 60 only. If we write extra, then it will not accept it. Now let's see. Here I have used for loop and I have written 20 data. Let's see in the waveform. Now in waveform, after 16, right, our FIFO is not accepting any further data. Initially, empty is 1, then it goes 0 after write, and full is 0, it goes 1 after 16 write. Underflow test. In underflow test, we attempt to read even if our FIFO is empty. For that, I have first written a single data, then we read 5 times. Let's see the waveform. I have written one data. Even if I try to read 5 times, now our FIFO is empty, it will not show any data. So observation is empty is 1 initially, then it goes 0 after 1 write, then 1 after read, then remain 0 after more read. So our underflow test is also passed. Random write and read test. Here we randomly generate the read enable and the write enable. If write enable is 1, then we randomly generate a data between the range 0 to 255, and if write enable is 1, then we read the data. Now let's see the waveform. Here we randomly generate the read enable and the write enable. If write is enabled, then we are randomly generate data between 0 to 255 and write into the FIFO, and if read is enabled, then we read it. Then data is coming out correctly. Wraparound test. For checking the wraparound test, first we completely fill the FIFO. Then we read half of it. Then we write 8 more items. Then we read the remaining. That's it. Waveform. Here we first completely fill the FIFO. Then we read half of this. Then we again put 8 data to the FIFO. Then we again read it back. Now our pointer is wrapping around correctly and giving the data correctly. That is first data is the first data to be out. Apply reset at middle. In this test, we have written some value in the FIFO and we apply reset at middle. Let's check its waveform. Here we have written some value in the FIFO. Then after some time, we apply the reset as high. We can compare its correctness by checking the empty flag. First, it is 1 when FIFO is empty. When we write some data, then it goes to low. After applying reset, then empty again goes to high. It implies that it is working fine. Simultaneous write and retest. In simultaneous write and retest, we make both write enable and the read enable high at the same time. Now, in my case, I have written some data to the FIFO. Then we take another for loop where I make simultaneous read and write. Let's see its waveform. First, I have written some data to the FIFO. Then I make simultaneously read enable as high and the write enable as high. But the data is coming out correctly when the read enable is high. That is the first data to be written is the first data to be out, and the data written it goes to the correct place also.
All right, so FIFO is a very interesting example of applying like design. It's like it's a module that it's just very often will be used. So I like here that they have used all the like all the steps to design it, starting from the design itself and the verification, right? Simulation, everything is covered. I'm just thinking of asynchronous, which make our life difficult. So asynchronous is much more complicated than synchronous. So I think better to use synchronous. FIFO. All right, let's go for it. Actually, he was okay. Let's go for this one.
The AI revolution is here. Can your data center keep up? Welcome to the future of digital twins. Request your free trial today.
I would like to free trial. Cadence is very interesting. A free trial Cadence Reliability. Cadence offers software platform for performance or design operation platform for data center through digital twins. Or these guys. Cadence related DC design enable engineer to design the next generation of data center inside and outside the physics based simulation powered by computational field dynamics. Guidance Reality Insight empower IT and facility management team to cooperate data center energy and perform optimization via web. This is very interesting. But yeah, one thing after the other.
Hey guys, welcome back to Explore Electronics Plus. In this video, let's understand FIFO and the design of FIFO, and also let us verify the functionality. Let us do the functional verification of the FIFO by writing the test bench also. First of all, before going to the details of FIFO, there are two types of FIFO. One is synchronous FIFO and other one is asynchronous FIFO. These two FIFOs are memory buffers. They are used to store and retrieve the data sequentially. It means whatever the data we have written into the memory will be read back in the same order. Means FIFO will give you the same order of what the write data are happened. If you are writing into the FIFO with the value 1 first and then 2, then 3, 1 will come out first, 2 will come out next, and 3 will come out next. Means the sequential data transfer happen in this FIFO. And the read and write operations, if they are operating with the same clock domain, means the same clock is governing for write as well as read, then we call it as synchronous FIFO.
And basically, for our calculator, we use the same clock.
If the read and write are happening with two different clocks, then we call it as asynchronous FIFO. Means in synchronous FIFO, with the same clock, we are operating write and read. In the synchronous FIFO, there are two clocks. One is for write as well as other one is for read. Means it is in other sense what we say, the FIFO is controlled by the subsystem at the means subsystem clock, which is operating for write, and the other subsystem is reading the FIFO that is operating with different clock, right? So here we are considering a synchronous FIFO with the same clock, and we'll be having the single clock in our design. Okay, and this is commonly used in digital systems where the buffer the data between two subsystems. They are operating under the same clock, but they have different data processing speeds. Okay, in such cases, we are using this FIFO. And means subsystem clock, it is in other sense what we say is for write, operating write and read. In the synchronous FIFO, there are two clocks. One is for write as well as other one is for read. Means it is in other sense what we say, the FIFO is controlled by the subsystem at the means subsystem clock, which is operating for write, and the other subsystem is reading the FIFO that is operating with different clock, right? So here we are considering a synchronous FIFO with the same clock, and we'll be having the single clock in our design. Okay, and this is commonly used in digital systems where the buffer the data between two subsystems. They are operating under the same clock, but they have different data processing speeds. Okay, in such cases, we are using this FIFO. And both write and read operations are governed by the same clock, and data is written into the FIFO in sequence and read out in the same order which is written, and ensuring the predictable data flow timing. Means whatever the data flow inside the FIFO and readout will be with the same.
If you're running your own business, you need Symphony.
And if you look at the FIFO operation, write operation and read operations are going to be carried using an internal write pointer and read pointers. So before going to the write and read pointers, let us try to understand the basic signals in FIFO. One is chip select. This CS signal is a chip select signal. chip select should be 1 to select this FIFO and operate on write and reads. Okay, chip select should be 1, then only we can operate this FIFO. And write enable is equal to 1, that is allowing the write data to go inside the FIFO. And read enable is equal to 1, allowing reading from the FIFO. And clock is a signal which is for the timing behavior. And data in is the data which is coming into the FIFO locations. And when we take out the data, it is coming out as data out. And there are two special signals here to indicate whether the FIFO is full or empty. Means full condition says the data what we have written into the FIFO for the all locations of the FIFO, then full condition will be 1. Means if full is equal to 1, the subsystems will come to know that the FIFO is full, we can't write more data into that. When empty condition is that FIFO is not having any value inside, the memory is empty. Means no data contained in the FIFO, then empty condition will be 1. And all the elements of the FIFO are all the memory elements are filled, then we'll be getting full condition. So here to get the full and empty conditions and enabling the sequential transfer of write and read data, we'll be having write pointer and read pointer. Means write operation is going to be operated with the write pointer and read operation is going to be operated with a read pointer. This write and read pointers are keep on incrementing when we are going to write and read the data from the FIFO. This is the basic idea of FIFO. Let us understand this in detail by taking examples of write and reads. Okay. First, let us look at write and read the sequential transfer FIFO. When empty condition is that FIFO is 1. FIFO for the all locations of the written into are empty. And when we take out the data, it is coming out as data out. And there are two special signals here to indicate whether the FIFO is full or empty. Means full condition says the data what we have written into the FIFO for the all locations of the FIFO, then full condition will be 1. Means if full is equal to 1, the subsystems will come to know that the FIFO is full, we can't write more data into that. When empty condition is that FIFO is not having any value inside, the memory is empty. Means no data contained in the FIFO, then empty condition will be 1. And all the elements of the FIFO are all the memory elements are filled, then we'll be getting full condition. So here to get the full and empty conditions and enabling the sequential transfer of write and read data, we'll be having write pointer and read pointer. Means write operation is going to be operated with the write pointer and read operation is going to be operated with a read pointer. This write and read pointers are keep on incrementing when we are going to write and read the data from the FIFO. This is the basic idea of FIFO. Let us understand this in detail by taking examples of write and reads. Okay. First, let us look at the empty condition, how actually in the FIFO. In this diagram, in the first diagram, if you see, the FIFO is empty. We'll be having 8 depth FIFO. There are 8 locations, but there is no data written into the FIFO. Initially, write pointer will be at the first location and also read pointer will be at the first location. Means to indicate the empty condition, we can compare the write pointer and read pointer. When they are equal, means write pointer is also at 0, read pointer is also at 0. We can say empty is equal to 1 and full is equal to 0.
This is my team, and we get everything done with Monday.com. Sarah is a senior project manager, and she has never.
And we start writing the data into FIFO. The first data is 12, next data is 35, next data is 40, and every writes happened, the write pointer will be incremented into the next location. After 3 writes, the data pointer or the write pointer will be at this location, but we are not doing the read operation. That's why read pointer is at 0th location itself. In this case, there are 3 data in the memory or in the FIFO. That's why full condition is also 0, empty condition is also 0. In the third case, you can see we are doing the read operation for the first 2 data. Means we took out 12 and 35 come out. Now the read pointer incremented to the third location, and we are not doing the read now. Means write pointer is at the 4th location, read pointer is at the 3rd location. Means these two are not same. That's why empty is equal to 0. In the next case, we are doing one more read operation. This 40 is coming out, and write pointer is at the same location and read pointer is also at the same location. In this case, what happens? The full condition is 0, and we'll be getting empty is equal to 1. So all the 4 data are, and in this case, what happens is at the same location. We're doing one not same. That's why empty is equal to 0. In is at the third, the read now. Means write pointer is at the 4th location, read pointer is at the 3rd location. Means these two are not same. That's why empty is equal to 0. In the next case, we are doing one more read operation. This 40 is coming out, and write pointer is at the same location and read pointer is also at the same location. In this case, what happens? The full condition is 0, and we'll be getting empty is equal to 1. So all the 4 data are taken out, and 4 data what we have written inside are read out. So this is actually 4. Why? Because we are at the 5th location here. So we are getting empty. So by looking at this, what we understood is we can get an empty condition is equal to 1 by comparing read pointer and write pointer whether they are equal. If they are equal, it says the FIFO is empty. Now let us understand the full condition. So the same example again. In the first diagram, you can see write pointer and read pointer at the 0th location. There is no data written into the FIFO. That's why empty is equal to 1. When we start writing the data, if you write first 3 data, the write pointer will be at the 4th location, and 3 values written inside the FIFO. No read happened. That's why full and empty are 0. When all the 8 values or 8 locations are filled up with the values, the write pointer will be keep on incrementing to the next location, and when it reaches the last, again it will roll back to the first location. It means what? First location, second, third, fourth, fifth, sixth, 7th, and 8th locations are filled up with the values. The write pointer has to come back to the 0th location. That is what the condition of FIFO is. But in this case, we need to indicate full condition. But write pointer and read pointers are exactly at 0 itself. Why? Because write pointer has completed all the writes and coming back to 0, but we have not started the read at all. That's why read pointer is at 0. But if we compare these two now, in the previous case, empty says read pointer and write pointers are equal, then empty is equal to 1. But now in this case, we completed all the write of the locations in the FIFO, but write pointer and read pointers are again at the same location, but it is giving 1. How actually it is giving 1? It should be empty, right? According to our logic, it should give empty. To avoid that confusion, we need to have one more extra bit to the pointers. So look at this last diagram here now. So without using the fourth bit, extra bit to the write and read pointers, what happens? The full condition and empty condition become same. It is difficult to implement the full and empty conditions. That's why after 8 locations are written, the FIFO pointer will be, write pointer will be incrementing, and it will be showing the value as 8. But there is no 8th value here. Obviously, it will come back to the 0th location itself, right? But at the comparison, or the value at the write pointer is 1000 and read pointer is 0000. The three LSB bits are same and the MSB bit is different. So comfortably we can compare these two by inverting this, okay? And we can say it is full. You can see this condition. We are comparing the read pointer and write pointer again, but by taking read pointer is equal to comparative operator, equality operator, double equals. We are inverting the write pointer of the MSB bit of the write pointer here, inverting this MSB bit, that becomes 0, and 3 zeros we are concatenating. So this value becomes 4 zeros, and we are comparing that with 4 zeros of read pointer. Then we can say it is full. If we take to represent 8 locations, 0, 1, 2, 3, 4, 5, 6, 7, 3 bits are sufficient. But if we take 3 bits, then it is difficult to implement full condition and empty condition. That's why we are taking 1 bit extra, so that write pointer will be incrementing to the next value 1000. And anyhow, FIFO is full. There is no content or there is no location to write the data. We can say it is full. But since the write pointer and the read pointer are internal, this 1000 is pointing to the first location itself. If we comfortably read all these and write pointer become 1000, it means write pointer and read pointers are equal. Then also we can say it is empty. Okay, let us understand this further using a Verilog code. So, and also let us write the test bench and simulate it so that we will understand it clear.
At the end of the day, when somebody asks me if they should be a network engineer, I would say if you have a system like Avik that allows you to see when something's down and react before other people even know something has happened, that is where you appear to be a magician, and that's where every network engineer wants to be a hero. That's what allows you to be one.
So this is my FIFO design. You can see over here, we have a design code. So this is my FIFO design. Module FIFO sync. And here I am taken 2 parameters, FIFO depth as well as data width. This data width is 32. This data width corresponds to each and every location of FIFO can store 32 bit of data. And FIFO depth 8 indicating we have 8 locations in the FIFO. Okay, since it is parameterized, we can change it. whenever we are using it in other modules. Right, in the test bench also you can change it and use the FIFO for any number of locations you want. And then input clock, input reset, here it is an active low reset signal, and we have a chip select, we have write enable and read enable signals to do the write and read operation, and then we have taken data in. This data in is of 32 bits, that's why 32 minus 1, that is 31 down to 0. Now it says it is 31 down to 0. Similarly, data out is also 31 down to 0, that is 32 bits. And we have output empty and output full conditions, these two flags indicating FIFO full and FIFO empty. Then we have a local parameter here. This local parameter is a FIFO depth log. It will be equal to $CLOG2 of FIFO depth. Means we are taking FIFO depth as 8 here. To represent these 8 locations, we require 3 bits to represent those locations. Means 000 to 111 is required to represent that many number of depth of FIFO. That's why I have taken a local parameter here to calculate the number of bits required to represent the number of locations. That is 3. This relog2 give us the number of bits in binary, that is 3. And then here is the representation of array for the FIFO. Register data width minus 1:0 means data width is 32. 32 minus 1 is 31 down to 0. That is 32-bit representation of each locations. And FIFO will be having a array size of 0 to FIFO depth minus 1. That is 0 to 7. Depth of 8, that is 0 to 7. It will be having, each locations are having 32 bits. Means each elements will be having 32 bits. And then we have a write and read pointer. You can see here, this is a write pointer. I have taken it as FIFO depth log minus, not minus 1. It is just FIFO depth log is to 0. It means 3 down to 0. It is a 4-bit pointer, right? But 3 bits are sufficient to represent them. We are taking a 1 extra bit, that is 3 down to 0. Similarly, read pointer is also 3 down to 0. That means it is also a 4-bit value.
Building something great takes more work than anyone realizes. Writing the code.
Right? Then we have to write and read operations, to carry out write and read operations. First, we need to check always at positive edge of the clock or negative edge of the reset. I said this reset signal is active low reset. That's why. And also we are making system to behave as asynchronous reset signal. So at positive edge of the clock or negative edge of the reset comes, we are checking whether the reset signal is 0. If reset is 0, the system reset happens and we are making write pointer is equal to 0. In the similar way, in read operation also, first we are checking for reset. If reset is 0, read pointer will be 0. Else what happens? We are checking for chip select is equal to 1 and also write pointer is equal to 1, write enable is equal to 1, and FIFO is not full. Then only whatever the data we are getting as input will be go into the FIFO and it will store, right? And once the first write operation is happened to this write pointer, we are incrementing the write pointer plus 1. Means in the first data will be come and sit in 0th location. And as soon as we do the write operation, we are incrementing that pointer to the next location. Similarly, by checking the chip select and read enable signal and FIFO is not empty, then only we need to do the read operation. If empty is there, we can't read the FIFO. If full is there, we can't write the FIFO. That's why we are checking for not of empty condition also. And also write enable is equal to 1. In that case, whatever the data present in that pointer location of the FIFO will go out as data out. And again, as soon as we read, we will be incrementing that FIFO to the next location. And here comes the write empty and full conditions I have explained with the diagram. So when the read pointer and write pointers are equal, we call it as empty. And read pointer is equal to the write pointer, but the MSB bit is reversed. Then we call it as full condition. This full condition and empty conditions works correctly. Let us verify that using a test bench. Okay, this is the end of our design, right? And now let me take you to the test bench. This is my test bench. Time scale 1 nanosecond per 1 nanosecond is sufficient here. Means 1 nanosecond indicating the delays what we are used over here will be with respect to nanosecond, and precision of the delay is nanosecond itself. Module TB FIFO sync is the name of the test bench, and the two parameters we are taken here also to represent the depth and width, and we are passing the value as 8 and 32. It is same we took in the design. And these are the registers which declared as reg for the input of the design and wires representation for the output of our design, right? And we are taken internal signal that has integer I. Let us see how it is used. Then comes your instantiation of the DUT. In the design, we have clock, reset, chip select, write enable, read enable, data in, data out, and empty full. We have connected all the signals to the variables of our test bench, right? Here the naming convention is used to connect the clock to the clock of FIFO, and reset n is reset n in the TB. It is same. The variables are same. That's why directly connected using the naming convention. You can also use the ordering connection also. Then we are generating the clock signal here. We are using a always statement and then begin #5 clock is equal to not of clock, it means for every 5 time minutes, the value of clock is changing. Means clock is toggling for every 5 time minutes. We can say the clock period is 10 here. And we need to assign the clock value before using it in always. But at the time of initializing itself, means at the time of declaration itself, we have initialized the clock value to 0 here. So clock will be start with 0 and then it will take a change to 1 after 5 time minutes. Again, after 5 time minutes, clock will be changed to 0. This line executes continuously until the simulation finished, right? Then I am using a task-based stimulus generation here. You can see this task is for writing the data and this task is for reading the data. Let us see what is there in write data task. Task write data. It takes an input of data in with the same size of 32 bits. Data width is taken as 32 here, right? So 32-bit data we are taken in D in as input to this task. Whenever we call this task, we need to pass a 32-bit data. And begin at positive edge of clock, we are waiting for the positive edge of the clock to come to enable the write transactions. Write enable is equal to 1 and chip select is equal to 1. and data in, whatever the in we are getting from the task input, we are giving that to data in. This data in is a variable of our test bench, and this data in is mapped to the input port of our design, right? This data in. So these two are connected. This data in and data in of our test bench component is connected. So that's why whatever the data we are getting in the task in din will be connected to data in. And we are representing, we are giving a display statement here that write data is this. And then in the next clock cycle, we are making write enable is equal to 0. It means whenever we are doing a write operation into the FIFO, we are taking 2 clock cycles here just for in one cycle we are writing the data. In the next cycle, we are making write is equal to 0. If you want to do the repeated write transactions, we can take this as, we can comment this and check. Similarly, in the read operation, we are waiting for the positive edge of the clock to come, and we are just making read enable is equal to 1 and chip select is equal to 1. Here, no need to give any other signals, just we are enabling the read enable, and whatever the data which is stored in the FIFO will come out in the sequential manner. But in the write data, we need to have data in input, okay, and we need to pass that data in. But in the read task, we don't have any input signal. We just triggering the read enable here so that the FIFO read starts. And again, waiting for the next positive edge of the clock to make read enable is equal to 0. Here also, whenever we are doing the read operation, it takes 2 clock cycle. In the first cycle, we will be getting the read data out. In the next cycle, just we are not reading the data. Okay. And now here, we are triggering the write and read operation. Initially, we are making reset is equal to 0 since our design is operating with negative edge, negative means active low reset. That's why for initially reset will be 0 and read enable, write enables are 0. And after positive edge of the clock comes, we are making reset n is equal to 1. It means we are coming out of the reset at the positive edge of the clock. Until the positive edge comes, the reset will be 0. This is the resetting the system, and here we are coming out of the reset. Okay, and we are just displaying the statement that whatever the data we are giving below are scenario 1. This is test scenario 1. What we are doing here, we are calling a write data task once. Again, we are calling a write data task. We are calling a write data task and providing the data input as 1, 10, and 100. It means we are writing 3 datas into the FIFO, right? 3 datas into the FIFO. So we need to read those 3 datas in the next subsequent cycles. That's why read data task is called. Again, read data task is called. Again, read data task is called. You can observe here, when we are going to call the write task, we need to provide the data in since it is expecting input data, right? When we are calling the read data task, no need to give any data since inside we are just triggering read enable is equal to 1, right? That's why this is having a empty parenthesis. This is having whatever the data we are giving into the write, correct? And then after this, we'll be giving, this is when we have to provide the data, task is called. Again, read, we are going to call the right. Right inside having a the write. You can see here, I am doing repeated write. I am reading immediately. Means if I am writing data, it is how be 8 times. Okay. Initially, I will is less than the repeated until the data in.
Is this your car insurance premium? This, even this?
They don't want us to that there's an easy way to lower your car insurance costs. What you do is you go to simplify.com.
Return 3 by condition data until the depth reaches. Writing is 8 times. And then to get a full condition, we are writing into the FIFO. We are not reading back until the depth reaches. Means we are expecting FIFO full condition here. In the next condition, what we are doing, we are reading the data from the FIFO until the depth reaches. It means we are expecting empty condition here. So now let us run this code and see what is the value we are going to get and what is the right values we have written over here should be going to the FIFO. This is the output for all the three conditions, three scenarios. Let us go one by one. In the first scenario, we have written three datas. You can see here, this is write enable and this is data in. We need to compare these two. When write enable is equal to 1, we are writing one value. And in the next cycle, we are making write enable is equal to 0. So comfortably in the first cycle itself, data will go and sit in the FIFO. After one more cycle delay, we are writing again. Means 10 will go and sit in the second location. Again, we are writing after one cycle. 100 is the value we are writing into the FIFO. After one more cycle of delay, we are making read enable is equal to 1 and write enable will be 0 here. You can observe write enable is 0 and read enable is 1. In this case, read pointer will be keep on incrementing and we are expecting 1, 10, 1, 000 as the output from the FIFO. You can see here we are doing read operation, read enable is equal to 1 and the first case itself 1 is come out. This one is come out. Right here, data out you can see. Similarly, the next value which we have written is 10, 10 is comes out. Next value which we have written is 100, 100 is comes out. This is our first scenario. From here onwards, we will be getting the second scenario. The second scenario is that
All right, so that was interesting about getting to know more in depth about FIFO in concrete example. Um, so I think the first step is to implement FIFO and simulate it and make sure it works perfectly. And then allo is very easy, but this is like the core of like not the core, but this is like a big assessment part of the task. So maybe this is the thing that needs to be done and in order to perform the task. So again, thank you so much for watching and see you next time.